Welcome. This is the second video in a series I'm doing about converting a 1950s era Seeburg Wallbox into a remote control for the music system in my office. So getting the old lock out turned out to be both an unexpected challenge and at the same time not as bad as I was worried it was going to turn out to be once I saw the challenge. First of all, you got to take this nut loose. That wasn't too big of an issue. But the next thing was to get this drift pin out because this shaft here is pinned into the lock, and you can't get the thing out without this. The rest of this is all riveted in. So what I did, there just wasn't enough meat on there to grab with the needle nose. So I came in here with the Dremel. I took and I cut a slot in the pin, like so, and then I was able to get my screwdriver in and wedge the pin out. Now, the pin will come the rest of the way out. This will come off. One would hope this will pull off. There we go. And we've got the old lock out. The new pin, or the old pin, is probably still usable. I only took a little bit of meat out of it to make that slot that I could get into there with. But my new lock did come with a new pin, so I'm just going to use that. This is the new lock. Came from needlesforjukes.com. So we're going to put that in, and then we will be able to operate our locking mechanism again. I'm going to rotate it so it points up. That way we can see what we're doing. Let's point this one up as well. I'm going to put on the nut. Let's just test fit this pin. Make sure it's all going to work properly. Looks good. And then we just have to kind of pound this pin in. Probably have to get myself a little hammer or something to do that. It's a little bit harder than the screwdriver's going to do. And I'm going to have to wait until the baby is no longer sleeping before we do that. So to make this a little bit easier to work with, I've wired up a connector here. This is a Mini Fit Junior, I think it's a Molex connector. Got a mating connector that I can hook it to. It's a 6-pin connector. 3 of the pins I hooked up to the terminal block, the 2 AC pins, and the signal out. The other 3 pins I kind of ran down inside. I don't know if you can really see it, but under here is the micro switch assembly for the quarter, dime, and nickel switches. So I wired each one of those, and that'll let me trip the quarter, dime, and nickel signals from my Raspberry Pi. I've also put together a little wiring harness here. This plugs into the connector in the Seeburg. Got my AC in via this big round connector, and power and control headers for my Raspberry Pi board. So it's time to sit down and design the Raspberry Pi hat that's going to interface with the Seeburg. This is going to let me both control the Seeburg's coin switches from the Raspberry Pi, as well as decode the output from the Seeburg on the Raspberry Pi, so that we will know what song selection is picked. Up, we've got power supply. So the power supply, I like to build these switching power supplies into my Raspberry Pi projects, so that way I don't have to worry about building a 5-volt supply someplace else. So this is your typical switching power supply. It's got an inductor, a couple capacitors on the input, a couple capacitors on the output, a diode. I do this in pretty much everything, barrel jack to power it, bridge rectifier. So this is going to take the 25 volts AC that we use to power the Seeburg and give us 5 volts DC that we can use to power the Pi. Simple enough, and then we'll bring it over here use it to power the Pi. This is Raspberry Pi header over here. Now we want to take the Pi and allow it to interact with the other components. Now you could just start wiring relays and inputs and stuff up to the Pi's GPIOs, but in most of my projects I tend to use an I2c Io Expander. This lets you use just 2 pins on the Pi, the SCL and the SDA, and you can interface up to 8 inputs. And the nice thing about this approach is that you can have many different hats on your Pi. These I/O expanders can be put at 8 different addresses, so you can hook up a lot of peripherals to a Raspberry Pi using only 2 I/O lines. So I tend to do that. It adds one more chip to the design, but it gives you that flexibility of just using 2 I/Os to the Pi, and then got all these other I/Os can be hooked up to other boards that need those I/Os. So this is the I/O expander. So now, next up, let's talk relays. So the relays are going to serve the same function as the coin switches in the Seeburg. Rather than putting in a coin, we'll let someone, push a button on an iPhone app or push a little switch or something to simulate the coin. The Seeburg can take 3 different coins, quarters, dimes, and nickels, so I'm going to go with 3 different relays. 1, 2, and 3. To make this a nice general purpose board, I actually ran out both the normally closed and the normally open contacts on the relays to headers. Relay boards are kind of useful to have around, so be able to use that for other projects as well. Now to drive the relay, so relay, even a little tiny dip relay is going to take more current than we really want to source or sync from our Raspberry Pi. So I'm going to use this ULN 2003 Darlington array. I've been using those in my projects for many years. What it'll do is you give it a pulse on this side, a high pulse, activate a Darlington transistor which will pull the output down to ground. So we want our relays to always have the positive side hooked up, and then the ground side we're going to switch. So relay 1, 2, and 3 hook up the outputs on this Darlington array. The Darlington array has built-in diodes in it, so we don't have to run a bypass diode for the inductive kick on the relay coils. That's built into the ULN 2003. ULN 2003, it can do a total of 7 lines. I only needed 3 for the relays. I took 2 of them and brought them out to a header. You never know what you might want in the future. And then that was a total of 5. The other 2 I just grounded. Now for the really interesting section, we have this down here. It's the signal conditioning. So this, I got the bulk of this circuit down here from the HEC Geek blog. That was another blogger who also converted his Seeburg. And what he noticed was the signal coming in from the Seeburg is really nasty, is glitchy, is AC, is noisy. Rather than do all of that debounce in software, let's debounce that in hardware, and let's also isolate it from the digital circuitry, so that we don't worry about, somehow our 25 volts AC gets in here and fries something. So let's isolate it, let's clean it up. So over here, this here, we'll go to the Seeburg. This is the 25 volt AC signal. So this is the one that's pulsed by that wheel on the side of the Seeburg as it goes off to count out the keys and send the signal to the jukebox, tell it which song to play. So that's nasty 25 volts AC. We're going to take that and run that through a bridge rectifier. The bridge rectifier will convert that AC into DC. It's not going to be nice, clean, flat DC. It's still going to be kind of lumpy, bouncing DC because it's an AC signal that's just been flipped, so it's all on the DC side. So we'll put a little bypass capacitor in here, a 2.2 microfarad. That'll clean that up a little bit, and then we're going to feed that into a voltage regulator. So this is a 7805. The HEC blog used a different regulator. I used 7805 because I just happen to have a pile of them sitting around on the bench. Any DC regulator that you can use to drive your optocoupler will probably work. So there's probably alternatives that would be cheaper than using a voltage regulator. For example, use a resistor and a Zener diode. You could probably get it down. But basically, we want to take these 25 volt AC pulses and get them down to a nice controlled voltage so that we can run an optocoupler without burning out our LED. So outside of this regulator is going to come 5 volts. We're going to put a current limiting resistor, 1K resistor, and that will drive the diode in the optocoupler. Now you've noticed this, there's no ground at all hooked up to this side, so this is completely isolated from the rest of the electronics. This optocoupler, the 25 volts, the nasty signal stuff from the Seeburg, never gets over here into the digital side. That's one of the benefits of using an optocoupler. So the optocoupler I used is a 6N138. It's a good beefy optocoupler. It's got 2 transistor drive on the output. I use this optocoupler because it's the same one that I use in various MIDI projects. So over here on this side, we're going to have the 3.3 volt logic side to the Pi. So the optocoupler, it's going to have a VCC of 3.3 volts. It's going to have a ground. This one, based on this transistor, gets pulled down via 220K to ground. So then the output of this transistor, it's going to be kind of like the Darlington array. When this activates, it's going to pull this down to ground. So we want is normally a pull up to 3.3 volts. So this output here will nominally be 3.3 volts. And every time a pulse comes in, pull that down to ground. Now then, there could still potentially be some noise, even on the outside of that optocoupler, even though we've conditioned it over here, conditioned it there, or we run it through the coupler, there could still be, a couple glitchy pulses. So we're going to use a debounce circuit. Now, a Schmitt trigger is a great debounce circuit for debouncing push buttons. I've already covered that, I think, in one of my other blog posts using a Schmitt trigger for debounce, so I'm not going to talk about it a whole lot here. Basically, the idea is there's some hysteresis in the Schmitt trigger, so that kind of like a dead zone in there, where if your signal's sloping, it's not going to bounce up and down like a normal TTL input would. So what we're going to do, we'll put a little resistor and a capacitor. That'll give us a little time constant on that. That'll cause a little bit of a slope to the signal, filter out any glitchy bounces up and down, feeds it into the Schmitt trigger. The Schmitt trigger is going to give us a nice, very clean output pulse, which goes back here, fed into the IO expander so that we can read that. There's plenty of other Schmitt triggers. It's a hex inverter Schmitt trigger. So I took 2 spare gates on it, ran them out to a header. In case we want to use push buttons, it's a handy place to put some push buttons. Added pull-ups for the push buttons. 3 unused Schmitt triggers over here. You can ground your unused inputs. That is my Raspberry Pi hat. There's one thing that I wish I would have done differently. I didn't realize this until I was trying it out, and I said, oh crap, what did I do? But one of the things about this IO expander is these outputs default to high. So when you power this sucker on, it's putting 5 volt, kind of a weak pull up to 5 volts in all of these, which goes in here to our Darlington, and it activates all 3 relays. So the power on state of this is all 3 relays are energized. That's, not in and of itself a huge problem, because these relays do have normally closed and normally open terminals, so we just use the normally closed terminal, and then we kind of invert the relay logic, and it all works. But it would have been handier for the power on state of this to be the relays were de-energized rather than the relays energized. So when I revise this board, I'm going to take these 3 spare hex inverters and put them right in there so that our power up state will always be to have de-energized relays rather than energized relays. It'll be a cleaner implementation. So here's the Seeburg hat for the Raspberry Pi. You can see I put a stacking header here to connect to the Pi. Over here on this side we have the switching power supply, so some relatively big capacitors, inductor, switching regulator, bridge rectifier, diode. This whole side here, I kind of designed it with holes so you could snap it off and get rid of the power supply if you didn't need the power supply functionality. For the ICs, we've got the 7414 Schmidt trigger hex inverter, the PCF9574 I2c Io Expander, and down here the ULN 2003 Darlington driver. The Darlington driver drives these three relays, which can be used to trip the quarter, dime, and nickel switches inside the Seeburg. Over here is header. 3 pins from each header hook up to a relay. Kind of designed this to be a generic board so that if I had other things I wanted to control with the relay, it could serve that purpose. There are footprints for LED statuses for the relays, but I haven't populated those. They're kind of in there. There's jumpers here to select the addresses of the I2c Io Expander. Down here is the analog processing section for the song selection signal from the Seeburg. So we've got the bridge rectifier, the 2.2 UF capacitor, 5 volt regulator, dropping resistor goes into the opto isolator. Out of the opto isolator, there's some resistors. We saw those on the schematic, and that'll end up fed into the 74 HCT 14 Schmidt trigger hex inverter. There's a couple headers down here for some unused outputs from the ULN 2003, in case we wanted to drive anything else. And there's also some inputs that hook up to the Schmidt trigger hex inverter so that we could, hook buttons up to that if we wanted to. And then the board, it piggybacks onto the Raspberry Pi just like that. You can see here at the end we've got the stacking header, some standoffs. I made sure to stand it off well above the shields on these connectors on the Pis. You don't want those to short out. So to take a look at the waveforms, I've hooked up some oscilloscope probes. I've got 3 channels currently hooked up. The first one will be on the raw AC, the signal coming from the Seeburg. The next one will be on the output of the bridge rectifier, so that'll be rectified. Then finally we'll have the output of the 5 volt regulator. Let's take a look and see what these look like on the oscilloscope. Okay, so let's trigger A3. A3. So what we see here is we see a couple pulses for the A, and then we see the pulses for the 3. So from top to bottom, first we have the raw AC, then we have the rectified AC, and then finally we have the 5 volt voltage regulator. So the scales are different. The top 2 are 20 volts per division. The bottom one is 5 volts per division. So up here on this one, there's really nasty AC coming in from the Seeburg. It's going rail to rail. Down here, out of the rectifier, the AC is getting rectified. Let me zoom in a little bit. So you can see here's the waveform, the raw AC. You can see because of the bridge rectifier, we're taking the bottom peak and we kind of flip each one of these up, so it smooths it out a bit. Because there's that 2.2 UF capacitor on there, it doesn't go all the way down to ground. We hold it about 7 volts on the bottom side, which is enough to drive our regulator. And then down here we look at the nice regulated waveform that comes out of the voltage regulator. It's got a nice sharp raise up to 5 volts, and then it holds 5 volts for the entire duration of the pulse. And then we've got a relatively steep drop back down to 0. So here I have moved the probes over to the output side of the optocoupler. So the first probe is on the optocoupler's output. That'd be this probe here. So the first probe, this one here, is on the optocoupler's output. Then the second probe is going to be on the debounce circuit, so on the debounce capacitor. And then the final probe is up here at the output of the Schmidt trigger that will be fed into the Raspberry Pi. Let's do A3 again and see what the output waveforms look like. Okay, so the top waveform, this is the output of the optocoupler. Every time the optocoupler trips, it will pull the signal down, so that's why you see the signal going down from 3.3 volts down to ground. The blue trace is the decoupling, the capacitor and resistor decoupling circuit at the input to the Schmitt trigger. So you can see just like this waveform up here, it's pulled down to match. And then finally we have the output of the Schmitt trigger that goes to the Raspberry Pi. So you can see each time there's a pulse, we'll get a nice pulse up to the Raspberry Pi. Nice and clean 3.3 volt pulse, devoid of AC artifacts. So there you have it. We can zoom in on that if we want. So let's zoom in on that. We can see a little bit more detail. Now we'll see the pulses in the debounce circuit. There's actually a bit of a slope that's due to that debouncing capacitor. But the Schmitt trigger will take that slope out and it will turn it into a very sharp up and down. So we've got this sort of perfectly debounced signal going into the Raspberry Pi. It will be very easy for us to write a program that decodes that I/O. Okay, so I've written the decoder Python program. To try it out, I've attached this LCD shield of mine that I've previously built for other projects. It's just stacked here on top of the stacking header on top of the Seeburg shield. So we've kind of got a triple stack. We've got Pi, Seeburg hat, and LCD hat. And we can use that to see the output of the decoder. Let me see, is that nice and readable? Can we get some lights off? Okay, you should be able to read that now. So if I hit A3, there, we've selected the song A3. Now I've also hooked the buttons up to this so that they will operate the coin switches. So the first button is going to trip the quarter relay. So if I push this, we will see the lights came on that said make a selection. Let's select G7. Selected G7. Quarter gave us 2 songs, so let's also select D5. There, so we've selected D5. Now the nickel switch is this one here. It'll trip the nickel relay. So we can see that turned on this light. This light here is the 5 cents inserted. You must insert another coin to make a selection. So even if we push some buttons, they don't do anything because we don't have enough credits yet. So what we can do, we can add a dime to that. And now we have enough to make a selection. So let's do N2. And similarly, if we insert a dime, that's this switch over here, then we get this light lit up. There's no stencil on the glass to tell what this one means, but I'm assuming this one means you've inserted a dime. You need to insert another coin to bring it up to 15 cents. So let's take our dime, we'll add a nickel to it. And now we've got the make a selection. So G9. Okay, I printed out my own title strips. I got this template to produce these online from a website called cdadapter.com. And they have several different templates. I chose this one because it was similar to the title strips that were already in the Wallbox. I'm a fan of 80s music, so I'm starting to populate it with various 80s songs. Next step will be to take these to the big cutter and cut them all into the right size pieces. And then we can put them in the title strip pages. Okay, so I finally got the Wallbox mounted on the wall of my office. This project's been going on for about a month, so it's kind of good to see it actually up there on the wall and operational. I have it integrated with my music player. Now you could integrate this thing with a variety of things. There's people who have integrated them with Sonos. I'm assuming you could probably integrate it with an Amazon Echo if you could tell the Echo what songs you wanted it to play. Haven't really tried that. I have my own player that I built myself several years ago that's a Pandora player, also a radio player by way of an SDR USB radio, and it can also play WAV files. So what I did is I just rigged up an API between the Raspberry Pi and the Wallbox and my music player so that we can play whatever songs we want. So the Wallbox is mounted. I did install a board on the wall so I could screw the board into some studs. This thing is really very heavy. So there's 3 screws that mount the Wallbox down to the plywood, and then the plywood mounted into the studs, so I can be relatively confident it won't fall down. Down below, sitting on the bench, is all of the guts from the Raspberry Pi, the power supply. I've got a couple buttons here. There's the white button and the red button. The white button I've rigged up to simulate a quarter being put into the Wallbox. The red button I've rigged up to skip a song, so that, you know, if you're playing songs and you want to skip past the one that's currently playing, you can skip to the next one. All of that, I've got a case, an acrylic case that I designed using Inkscape, and all of that is going to go in a little acrylic box. It's going to sit down here below the Wallbox. We'll put the buttons in and a vacuum fluorescent display. So if there's enough material for a third video, once that case is ready, I may actually do that. And then we'll see the additional, you know, Raspberry Pi electronics being put somewhere else other than a pile on the table. Anyhow, let's try it out. So flipping through the pages. Now there's a spring that's supposed to be in here. That's supposed to like hold page 1 open. A lot of those springs are broken in old Wallboxes, this one included. I don't know why you actually need that spring, because the whole thing seems to work just fine without it. So I've got this custom labels for all my 80s music. Going all the way back here. The very first page. I've rigged up with some royalty-free stuff and some other stuff like test tones and radio stations. As I said before, my player it has an SDR radio built in, so I can play radio with this. I wanted all of this selectable from the Wallbox. So we've got some royalty-free music that I can play on here without YouTube getting upset about copyright. The royalty-free artist I typically use in my videos is Kevin MacLeod. We'll link some of his information here. And I've got, looks like 8 of his songs set up in the Wallbox. So I'm going to push the white button, which will simulate a quarter. So there, we can see the Make Any Selection lights have lit up. We can pick a song. I'm going to go with N6. N6. And now it's sending an API over to my music player and telling it to play that song. So it's playing Exit the Premesis by Kevin MacLeod. And let's say we want to queue up another one. We can hit P6, that'll be MetalMania. Now it's queued up, but it's not going to play it till this song is finished. So what I can do is I can grab my song skip button, the red button down there at the Raspberry Pi, and now we've skipped to the next song. So now we're playing MetalMania. So I hit skip again, and there's no more songs queued up, so it's just going to shut my player off. Now we're out of credits, so if we push these buttons, nothing happens because we need to put some credits in. So just because we can, we angle this up, I'm going to put an actual real quarter in this. There. Well, that's unfortunate. It ended up saying it wants 5 cents, deposit another coin. That's not what we wanted to happen. So yeah, somehow I put the quarter in and it registered it as Registered it as a nickel. Oh well. Let's fix that. So there, I've simulated a dime. We can play another song like a U6. Let me try queuing up some more songs. So we could actually, the way I've designed my player and the API between them, we can queue up an arbitrary number of them. So let me do Q6. Then we'll do R6. Add another quarter. Let's do S6. T6. Do another quarter. U6. And V6. These are all more Kevin MacLeod songs. So we don't want to sit here and listen all day, so let me just skip some of them. So now here's the next one that was queued up. Here's another one. Okay, so that's the basic functioning of the Wallbox. As I said, I'm going to get the Raspberry Pi guts is going to go down here. We'll have the push buttons here to skip the songs and simulate the quarter being inserted, and then a vacuum fluorescent display to show you what songs currently being played. I think that's handy to have that, and I'll add a volume control too. So maybe there'll be enough material for the next video. Thank you for watching my video. Please visit my website at www.smbaker.com for more electronics projects and sandrail stuff. Bye.